Hello and welcome. In this video lesson, we're going to take a look at a method called separation of variables. So as we have already mentioned, the goal of an analysis of any ODE is to establish a clear relationship between y and t, even though you start with a model for the rate of change of y with respect to t. So often we'll write this notation here to indicate a first order differential equation, and this is just suggesting that dy dt may depend on both the independent and dependent variable. In translation, that just means that the right-hand side of the equation may have both t and or y in it. So there are actually three forms of analysis that we typically conduct, and separation of variables is one specific variation of one of these three types. So oftentimes, many differential equations are not solvable, especially as they become nonlinear, and we'll discuss what all that means in a later video. But you have a qualitative analysis, and what you're doing with the qualitative analysis is you're trying to study the general qualities of the solution. So for instance, a qualitative analysis might indicate, well, if y and t are bigger than these values, then dy dt is positive, or y is increasing if it starts off at a value of 3 or bigger. So that's qualitative in the sense that it describes what will happen, i.e. y is increasing over time, but it doesn't really tell us specifically how. Then a slightly more useful analysis, oftentimes, would be a numerical analysis, where what you're doing is you're in some way taking advantage of what you know about the differential equation to generate basically a set of ordered pairs over time. So think about numerical analysis as you're estimating values. So you are actually estimating values of y over time here. In step one, you're really not doing that. You're kind of just generally describing what will happen under certain circumstances. And then the most powerful, the one that we want to aim for, is the analytic analysis. And here, this is really what we did in Calculus 2. We learned how to solve differential equations, or basically take antiderivatives and go through the integration process to get the original y function back. So we're going to focus on one variation of number 3 here. But before we do that, let's actually discuss what we mean when we talk about, well, what is a solution to a DE? We maybe know how to find them from some of our Calculus 2 techniques, but what does it really mean once we've found it? So a solution to a differential equation of this form is a function, y of t, that makes the equation true. This is kind of like what you would have done in algebra, where you might have said, okay, well, let's look at the equation 5y plus 10 equals 20, and I might argue that y equals 2 is a solution to that. And the way you would check that is you would say, well, let me put in a 2 for y here, and if I put in a 2 for y, 5 times 2 plus 10 comes out to 20. Oh, and that's exactly what I was expecting. 20 does equal 20, and therefore y equals 2 is indeed a solution to that equation. But when we're talking about differential equation, the distinction is that the solution to this is a function that makes the equation true. Just like in solving an equation, an algebraic equation, the value, the numerical value of y that makes it true is what we call the solution. So put more practically, a solution takes a rate of change model for, say, the change in ELK per change in unit time, and gives us a function that describes the number of ELK as a function of time. Okay, so it does not only satisfy it algebraically, but it also leads us to going from a rate to an amount. So if you think about a derivative as a speed, then its antiderivative is kind of the distance at any moment. So how do we check, for example, is y equals ce to the 0.01t a solution to dy dt equals 0.01y? Well, first of all, c is our arbitrary constant, so that's the same thing that we would have learned in Calculus 2 class. In order for this to be a solution, what we're saying here, let's interpret this. The derivative of y, and I won't say with respect to t, we'll just assume that that's the case. The derivative of y with respect to t must equal And I'll put a little must above this equal sign to emphasize that we're saying in the English language that the derivative of the function that we find must equal 0.01 of the original function y. In other words, we're looking for a solution that when you take its derivative, what you get is just some scalar multiple of the original function itself. Well, exponential functions, if you think about it, when you take the derivative of an exponential, you still end up with some multiple of your exponential. So here's how we handle this. We, first of all, in order to plug things into this equation and see if this makes it true, I'm going to need its derivative as well. So the derivative of my equation, the derivative of this using the chain rule, will be 0.01 c e to the 0.01 t. Now what I want to check is I want to check that when I plug in for dy dt, I'm going to plug this in right here, 0.01 c e to the 0.01 t. Does that equal, I'm going to put a question mark above that equal sign, 0.01 times y? Well, what is y? Well, y is the original function that we're claiming is the solution here. So I'm just going to replace y with c e to the 0.01 t. And now let's, simplify, quote unquote, both sides. The left side, there's not really much I can do. I can remove the parentheses on the right side, and lo and behold, these two sides are in fact equal to each other, and therefore the answer is yes, this is a solution because it makes the equation true. Just like up here, y equals 2 made the equation true. Let's look at another one. Is y equals 1 plus 2t a solution to this messy ratio y squared minus 1 over t squared plus 2t? So again, the first thing we need to do is if we claim that y equals 1 plus 2t is the solution, then I need to find its derivative because I'm going to have to plug in the derivative of that function. This is where this varies a little bit from what we used to think of as a solution. When we plugged in y equals 2, we didn't have to plug in any function of y equals 2. We didn't have to take its derivative. But with differential equations, it's that extra layer of complexity. Now the derivative of 1 is 0, the derivative of 2t is 2. And so now I have to say, okay, well for dy dt, if I plug in 2, does that equal the right-hand side? Well, y is 1 plus 2t, so I have to replace y with 1 plus 2t right here. That's squared minus 1 over t squared plus 2t. Well, those don't look the same, but I probably know that since there's a fraction here, something may cancel out, so I'm going to keep working on this and kind of massaging that right side. So if I FOIL 1 plus 2t squared, I'll get 4t squared plus 4t plus 1. And then I'll have minus 1 over here, that's that minus 1 right there, all over t squared plus 2t. Alright, so again, I'm not sure yet whether these two sides are equal or not, but I do see that here I'll have a cancellation of a plus 1 and a minus 1. So I'll have 4t squared plus 4t over t squared plus 2t, and I kind of see that they both have the t squared in there, but the top doesn't quite look like the bottom, so it's not like I can cancel out a t squared plus 2t. I could factor out a 4 from both terms in the top and make this t squared plus t over t squared plus 2t, and that clearly will not cancel out, right? T squared plus t will not cancel with t squared plus 2t. Therefore, these are not going to be equal to each other, and so our answer is no. 1 plus 2t is not a solution to this equation. Now let's suppose we take a look at another possible solution candidate for this differential equation. Same differential equation, but now we're going to check if 1 minus t over 2t plus 1 is a solution. So I've got to find the derivative of this guy. And this is just a common step in checking solutions. If you had a second derivative in it and you thought you found a solution, it might be the case that you need to take the second derivative of y. Okay, so in order to find this guy's derivative, I have to use the quotient rule, which is derivative of the top times the bottom So f prime g, which the derivative of 1 minus t is negative 1, times the denominator, which is 2t plus 1, and then minus the derivative of the denominator, which is 2, times the numerator, which is 1 minus t, divided by the denominator squared, which is 2t plus 1 quantity squared. Now I'm going to clean that up a little bit because I know I'm going to have to reduce things later on anyway. So here in the top I'll have negative 2t, here I'll have positive 2t, so the 2t's will cancel out. Then I'll have a negative 1 and a negative 2, which I believe comes out to a negative 3 there, and all over the square of this. For now, I'll go ahead and leave that alone. I may not have to FOIL that out after all, but let's go ahead and check. So now we're going to go ahead and plug in for dy dt. In this equation, we're going to plug in for dy dt what we just found as the derivative of our candidate solution. And we're going to check, is that equal to the square of y? Okay, so the square of y is going to be the square of this function. So 1 minus t over 2t plus 1 quantity squared minus 1 over t squared plus 2t. All right, so as we proceed, let's go ahead and do a little bit of analysis on this guy here. So first off, if we square both top and bottom, then the square of 1 minus t, if we were to go ahead and FOIL that out, we would get t squared minus 2t plus 1. And the square of 2t plus 1 is going to be 4t squared plus 4t plus 1. And we have our minus 1 all over t squared plus 2t. Now one thing that I can do here is find a common denominator. So I'm just going to continue on over here. I'm still checking about this equality, so I'll just write question mark equals, and I'll get a common denominator here. So minus 1 you can think about as 4t squared plus 4t plus 1 over 4t squared plus 4t plus 1. So in this case we have to do quite a bit of algebra to massage this down. And minus 1, like I had mentioned, is just going to be, we'll write that as 4t squared plus 4t plus 1 over 4t squared plus 4t plus 1. That's just getting a common denominator. And now we can subtract the numerators. This is all over t squared plus 2t. So you can see this just can sometimes involve quite a bit of algebra. T squared minus 4t squared is minus 3t squared. Negative 2t minus 4t is negative 6t, and 1 minus 1 is 0. And this is all over 4t squared plus 4t plus 1. Whoops, let me try that again. 4t squared plus 4t plus 1, all over t squared plus 2t. Now, because I'm going to have a fraction divided by something, I'm going to be able to multiply by the reciprocal of t squared plus 2t, so which is 1 over t squared plus 2t. And we're getting closer. I actually see that if I were to FOIL out 2t plus 1 squared, that would be 4t squared plus 4t plus 1. So I see that my denominators are the same here. The question is, will these cancel out and give me the negative 3? Well, in fact, I see that I can pull out from the numerator, I can pull out a negative 3 from both terms, which will then just leave me with negative 3 times quantity t squared plus, let's see, where were we there? And this guy would leave me with a plus 2 because we had a minus 6 there. And we can see that both of these terms cancel out, these factors here and here. And I am, in fact, left with negative 3 over 4t squared plus 4t plus 1, which is exactly the same thing that I have on the right-hand side. And again, I just had all these question marks above the equal sign. That's just a way of setting things equal to each other with the knowledge or with guarantee that you're not claiming that they're equal, you're checking to see whether or not they are. And in this case they are, so therefore the solution up here that's been found or been given to us is in fact the solution to that differential equation. So we saw in number 2 that 1 plus 2t wasn't a solution because you didn't get the left and the right hand side equal to each other. It was not possible. But in number 3 it was possible to do it.